Today we are getting back into a little bit of AI, and we're going to talk about some the search problems that we were working on. We're also going to I'm going to catch you up on what I was able to accomplish off stream, and then after that, we'll move into what we're actually going to do today, which is basically going to be a little bit of maintenance work. We're just going to clean things up, make things faster, and yeah, just start explaining it, I suppose. All right, first things first, you should be aware that I moved everything into the repo that we have on GitHub. This is under GitHub slash culture dash of dash development. And there's this repo called fast. And this is basically everything that I've been working on stream for the last few weeks. And now the other big thing is instead of having everything named like, just search or search problems or just BLOS, I renamed everything to be like fast.blos or fast.search. And the reason for that is just so that the names that get built of the DLLs that get output have a name that is representative of the actual namespace that's in them. And it also makes the test environment a little bit easier to, like, the test explorer a little bit easier to go through. Oh, that's another thing. I added tests. I decided to add a test project for a unit test project because it makes it running small little increments of code just kind of a lot faster and a lot easier. There's also some really nice integration here with Visual Studio Code when you have XUnit running. That will just let you run like an entire class full of tests, or it'll let you run just a single test. So like, for instance, I can run all the tests in this project and it'll run a build before it actually runs the test. And you can see they all passed. And it gives you an output for each and every one of the tests. Or if you want to, you can just run a single test. And again, it'll build. And it runs just your one test, and everything's kind of nice like that. So this is one thing that I want to do. Previously, what we had was this, like, here's a test function, here's another test function, and I was commenting the ones out that I didn't want to run, which got kind of, turned into kind of a pain. Instead, what we're going to do today is actually move all of this stuff into the test project. We're going to turn this from being an actual application into being just a library, and then the test will be like the driver that runs everything. And that's like the main thing that we're going to get done today. And then we're also going to fix up a couple of like bugs with this. In particular, let's take a look. Let's talk about A star and breadth first search. So first off, one of the things that I noticed so I showed this to a couple of friends of mine, and they all generally, even though they had not talked, sort of had the same idea about like what the problems were. And it turned out that the problems were basically that when you compared this to things like Wikipedia, it didn't line up very well. And then there was also this big issue where we were somehow searching through trillions of states in order to find the goal, when in reality there's only like a couple 100,000 states. 9 factorial divided by 2. Yeah, there's only like 180,000 states, and somehow we managed to search through trillions of states in order to find the goal for this, which was kind of a pain and not really what we expected. So let's just go take a look at some of the changes that I made. First off, in breadth first search, you'll notice that our open set was still here. And what I did was I added this thing called a closed set. And the way that a closed set works comes directly from Wikipedia, right? Anytime that you are about to add a child, if it's in the closed set, you just say, you know what, I have already explored whatever the best possible path to this is, so I don't need to add it to my open set again. And now what you end up with is something like this, where it runs breadth first search, and then hey, guess what? We actually solved our problem now. We solved the hardest 8 puzzle state, which has 31 moves to reach the final solution, and that's the optimal way to do it. But you will notice that we're still exploring 520,000 states, and we just showed that there was only like 180,000. So this is sort of a bug, but there's a pretty quick explanation for it, and this is going to be one of the things that we fixed today. But let's go ahead and talk about what we did accomplish, which is actually finding this. So already some success. Hello and welcome to the stream. I'm just hanging out talking about AI right now. I'm working on search problems, but happy to talk about whatever. Feel free to drop a line in chat. If you're lurking, that's totally cool too. Other than that, yeah, just drop me a line, and I'm just going to keep going. So the other stuff that we want to do is move all of the program stuff into unit test, fake unit test, of course, because we're not actually using them as unit tests, just a way to run small bits of code without having to comment a bunch of stuff out. And then also we want to change the search project from being a program to being a class lib. All right, implement this, improve the nodes explored by orders of magnitude. All right, so this was something that we started on last time, and we had only doubled it, but we're gonna come back around to this maybe today, but probably not. All right, so let's see. First things first, why are we searching through 520,000 states when there's only 180,000? Well, that actually comes down to the way that this min heap was implemented. This min heap was implemented such that it is not a set, right? When we talk about a set, what that means is you can only have one value in there one time. And the min heap that we implemented allows you to add the same state multiple times, and it doesn't dedupe them. So if we try to add the same state 2 times before we add it to the closed set, then it'll still add it in there multiple times, and that's why we're ending up with this problem. So what we want to do first is we want to switch this over to being a set, and then we want to basically just swap out the implementation here, and this should just clean itself up. So let's talk about a set. I actually implemented one, and this one is called open set because again, I wanted to follow along with what it looks like on Wikipedia, so I just named it the exact same thing that we have there. And the way that this works is there's really only a few things you can do. You can check whether there's stuff in there or not. You can push something to it or try to improve it, right? So no matter what, we're going to say, hey, Q, this is your problem, and here's the new state, and here's the new cost for this state. Add it to it if it's not there, or if it's an improvement because it has a lower cost, then replace the old state with this new state. And then the other thing that you can do is you can grab the minimum state and actually remove it from the queue altogether. So let's take a look at this right here, which is push or improve, because this turned out to be the thing that was like the most challenging to implement. First off, in .NET land, there is a sorted set implementation. This sorted set implementation sorts things by the same key that it uses as like a as like the set value to determine whether or not something is in the set. So we have to do some magic around here in order to actually get it to do what we want it to do, and we'll come back to that as soon as we get there. So yeah, when we create it, all we're doing is doing this, and then we're telling it use this magic way of comparing 2 items that we can now implement the logic that we want, which is if they have the same state, then they are the same no matter what the cost is. And only when the state is different do we want to sort them. When the state is the same, then we're going to use that to compare whether or not they need to be changed. Okay. And the way that that happens is literally you just check the state, you get the hash code of it, and if the hash code is the same, then you return 0. Otherwise, we go take a look at the cost. should be noted right here that get hash code always returns an int, which has a range of, only like what 4 billion or so. So there is a limited number of items that are really 2 billion, because half of them are negative. Oh, I guess you can have negatives. Yeah. Anyway, so the idea being that like we can only ever have about 4 billion items in this thing. Now for like for resources on your computer, that's pretty limiting. Having more than 4 billion things in memory at any given time is just a difficult thing to do when the state size is non-trivial. So this isn't that big of an issue, and we're gonna have to work around this anyway, because the problem that we eventually want to solve is basically the state size is the full size of the memory on our computer. So we're gonna have to come up with a new state representation that sort of tells us a better way to go about this. All right, next here we have, let's see. All right, so if they're the same, then we say they're the same, which is 0, based on the state only, not caring about the cost. The next thing that we do is we check whether or not, if they are not the same, then we order them by the cost. Now this was something that actually took me a long time to get right. I spent a number of hours looking at this because originally I had this as just less than. And what ends up happening here is when you have a set that is ordered, it can't just look at the hash value and go find that location in some array. It has to actually search, and it's storing everything in a binary tree. And so the way that it goes about doing that is it looks at the value and will traverse down one side of the tree or the other. And when you have just less than, it can traverse down the incorrect side when the top two nodes have the same cost. But if you do it less than or equal, then it will always find the one that's at the root, which is the primary use case here. And it will always find the one that we care about. So this is important, and I say always, this is something we should probably come back to do check if this always works or not. Okay. And then what else do we want to do here? So that's the way that we actually store things in the set and get them to order correctly. Now push or improve says, all right, go see if this thing is in there. If it is, give me the value of it. And if it is in there, then we're going to compare the cost. If the cost is an improvement, then we're going to remove the one that's already in there and add the new one. And if the item is not in there at all, then we're just going to add the item, period. And then getting the top is pretty simple. You just make sure that it's not empty because you can't pop from an empty set. And then you grab the min item, which is a constant time lookup. You remove the min item, which is logarithmic time. And then you just return the actual state from that, which is what we're looking for. All right. Okay, that's perfect. Save this. Got my little note in there for the to-do. Now, this set is what we want to use to replace in breadth first search. And the way that we're going to do that is a little more involved here. We have to actually, let's go ahead and extract this. We're going to come back over here. We're going to have this thing called new state cost struct state cost.cs. Yep. Namespace fast.search. All right, the idea here is we don't want to call it this anymore. Public struct, and this one needs to be state cost this is a bit of a hack right here, and we'll come back to that in just a second. Using system. Okay, so now everything works. And let's go ahead and replace this one with state cost. State cost, state cost. Okay, back to breadth first search solver. We want this to be an state cost open set, and we want this to be a state cost, and there is no size for this. Okay, now we need to push or improve. New state cost, or state cost equals pop min, var state equals state cost dot state, var cost equals state cost dot cost. All right. Now we need to create a new state cost, push or improve. Okay, and I think that should do it. I think that's going to do it. Let's see here. Does it build? Hey, all right, it builds. And the fun one, does it run? That appears to be busted. No, all right, okay, so we still did way too many evals, so we definitely have an issue here still. And this leads me almost directly to thinking that this is not 100% valid. Which is not fun. It basically means that that's not fun. That's great. That is so great. Okay. All right. So this is not valid. Spoiler, it's not valid. But we did still find the solution. It was really slow. Let's see if it runs faster the next time. We're doing about 164,000 states per second. Okay. Well, that's not fun. Okay, anyway, we'll come back to this in just a moment. For the time being, what I want to do next is go take a look at the A* search and talk about the other improvement that I made here off stream, which is I actually implemented different heuristic functions, and you pass in the heuristic function when you tell it to solve the thing now. And when you tell it to, you can pass in whatever heuristic function you want. I put the heuristics all on in_puzzle. And we see down here that we have the Hamming distance, which is the one that we have been using, and then I have also implemented the Manhattan distance. Oh, crap. The Manhattan distance. So the Manhattan distance, again, just says that you want to track all of the number of moves that any given tile except the blank space is guaranteed to have to move. So if, for instance, the 1 needs to be in the top left-hand corner, but if it's down in the bottom right-hand corner, then it has to go up 2 and over 2. So you know you have to move the 1 at least 4 times, and you can add 4 to your solution. And what this does is it gets you much closer than the Hamming distance to the correct number of moves. that have to happen, and this should reduce the overall number of states we eventually have to evaluate. And let's just go take a look and see if that happens. Program. Anything can happen now since the underlying part of it is not valid. All right, we do .NET run and we see that it has to build, has to actually do the search. Okay. All right, so we started with breadth first search, finds the correct moves, finds the optimal, does it in about 475,000 evals. Then we moved on to A star using the Hamming distance, and we see that because it is choosing something, it can eliminate a lot of possibilities, especially as the search gets later, right? So this is one of the things about using A star is you expand. In fact, let's just take a look at it. Here's what it sort of looks like visually. Is you have this giant thing right here, which is your start space, and then you have this thing over here, which is your goal. And the way that it works is you're going to basically create a circle around this. This is breadth first search. 2 steps away, 3 steps away, 4 steps away, 5 steps away, right? 6 steps away, and eventually you get there, but you have to explore this whole screen before you can get there. And then what happens next is we try something like A star search with Hamming distance, and what it does is it says, okay, all of these states, these first level states, are pretty close, but then it knows that as some of them start to get closer, it does it like this. And this stays pretty fat down here, but it makes progress toward the goal each time, right? And you'll notice that now there is a large area all up here, all down here, and all around that we don't actually have to explore. And as your search gets better, let's get another color. Can I find like a green? As your search gets better, it's yellow, orange. What's a color that would look good right here? Anyway, as your heuristic gets better, what you end up with is something that starts going more and more like this, right? We don't need to search backwards nearly as far, and we make larger steps forward each time. So this right here is our heuristic getting even better. And what you see is that we're basically trimming all of the stuff around here, and just making progress toward the goal a lot faster. So we're exploring a lot fewer states. And then we have this idea of a perfect world, which we're going to use something super bright like cyan. No, that's not going to work. Like this bright blue, like this bright yellow. I don't know, can you see any of this? How about if we make it super thick? Then you can definitely see it. Like 8. All right, so this is your start state, this is your end. And then once you have a perfect heuristic, you explore just the states on the goal path. And so this is very few number of states, even in a very large state space. So once we get up to something like the 15 puzzle, which is this exact same puzzle only on a 4x4 grid, you now have 15 exponential divided by 2 number of states. So you have 653 billion states. There is a black screen. This is a black screen only. I am not seeing a black screen actually. Even on my preview, I still see everything that I'm looking at. Can you tell me exactly what you see? Also, thanks for coming. You don't see anything at all. Um, wow, that's really interesting. Like I said, in my preview, I'm actually seeing all of my stuff. I am, yeah, I see my preview. I'm looking right now, I'm drawing in Paint, and you just see a black screen. That's it. Okay. Well, I don't know how to improve that. I don't know how to fix that. If I switch over to code, can you actually see me writing code here? I'm from tablet. Let me check PC. Oh, okay. Well, if it's not working on a PC, that's something I need to improve anyway. Or rather, if it's not working on a tablet, that is one of my favorite ways to consume content on Twitch. At least I got my mic going. I've made that mistake twice. Okay. In the meantime, I will get back to what it is that I was taking a look at. All right, so you explore only the nodes on the goal path. Well, it's just a problem on the tablet. Okay, well, thanks for that information. I do have a tablet, and I will put this together and see if I can get this sorted out after the stream today, so that from now on you can view it from a tablet. Because like I said, that's my preferred way of looking at this as well. Well, to catch you back up now that you can actually see what I'm talking about. So if this state over here, I guess I should make it nice and bold. So this state over here is your start state, and then this state over here is your goal state. And these different lines represent the way that the search actually expands in the space. A breadth first search are these red lines where it's basically searching it in all directions out from you because it has no idea where the goal is. It has no concept of how far it is from the goal or what direction the goal is in. So it is literally just trying every single possible state, the shortest path that it has reached so far. And what you end up with is you end up checking a large area full of all kinds of fruitless states that are not anywhere near on the path to where you're trying to get to. The next one is the blue one. This is something where it's still really fat, especially over on this side. Um, and now that we have a bolder one, let me just go like this. So this would be something more like what was I talking about? I just lost my train of thought. This would be something like Hamming distance, where it's still really fat, but you can see it start to make progress in the right direction. Like this. And what you end up is not searching too far over here off to the left, because it will realize very quickly that those are getting further and further away from where it's trying to go. And then when you move on to, say, the green ones, which would be something like the Manhattan distance, you start to get very narrow and making large progress towards your goal with each additional step that you take. And you can see that the total area inside these different circles, like the total area inside this green space is much smaller than the total area inside this blue space, which is even still much smaller than the total area inside the red space if I were to actually expand the screen out large enough to get the red circles all the way over here. And the yellow here is actually kind of liking this. Let's go with an orange maybe. Orange? Why are they all dark? Orange? Can I just get an orange? No, I can't get an orange because I don't know where the orange is. Whatever. Orange. There we go. And this right here would be if you have a perfect heuristic, you only expand nodes that are on the goal path. That is basically the definition of a perfect heuristic. And perfect heuristics do exist. They're very difficult to calculate for most problems, but they do exist. To give you an example for this one, we could calculate a perfect heuristic for the 8 puzzle by taking an array of all of the possible states and then just putting in the exact value of the maximum number to get to the goal. And what you end up seeing is you will only ever expand nodes that are directly on the path to the goal. And that's sort of, when you get to really large state spaces, you need to get as close as you possibly can to a perfect heuristic as possible, or you have almost no chance of like solving the problem that you're trying to solve. And so that's what we're doing. We're taking a look at a couple of different heuristics to see how they improve it. Then what we're going to do is learn how to calculate heuristics for problems given just a problem definition. And then eventually we want to apply this all to our really big problem of improving the speed at which we can do dense matrix multiplication on a computer. So that's really kind of the path that we're on here. And this, again, is just, the different heuristics, and now we can actually see a representation of it. So we did BFS first, and we saw that it expanded a lot of nodes, 475,000, and this is a mistake. We have to fix the open set implementation so that this only expands the ones that it's supposed to. And then we have the initial state, which is... I'm sorry, and then we did the Hamming distance, which again just takes account of the number of tiles that are out of place, and then adds those up. So the maximum heuristic value, if all of the tiles are not in the correct place, it will add 8 to the score. And this can actually get you quite close, right? So as you get deeper and deeper into the search, this is what I was doing. All right, as you get deeper and deeper into the search, you can see that it no longer expands up and down very much. It always makes very, very, very quick progress toward the goal as you get later in the search. And the reason for this is just because back here, a lot of values, are going to end up being less than the real value. So it has to get pretty wide near the starting point. But as you get closer to the goal, your heuristic value will start to cut off a very large portion of the states that it knows aren't good states. All right, and that's what we see. So as it gets closer, we evaluate significantly fewer than doing breadth first search. And then when we do the Manhattan distance, which is calculating the total number of moves that you're guaranteed to have to make, period, under the assumption that we're not just counting the number of tiles that are out of place, but the number of moves that an out of place tile will have to make in order to reach its goal. And in this case, we get down to evals just orders of magnitude lower because it's a much better estimate. We know that the real cost is 31. And for the starting state right here, what we see is this 8 has to move over to the right and then down 2, so that adds 3. The 6 has to move over to the right and down 1, so that adds 2 more. The 7 has to move down 2 over 2, so that's now 9. The 2 has to move right 2 and up 1, so that's 10, 11, 12. The 5 is actually... the 5 is in the right spot, so we don't add any there. The 4 has to move over 2, so that's 12, 13, 14. And then the 3 has to move up 2 and over 2. So that's 16, 17. Oh, wait, no, we were at 14. So 15, 16, 17, 18. And then the 1 has to move all the way to the top left-hand corner as well. So that's 22. And we know that the answer is 31. So we're starting immediately saying, I know you have to make at least 22 moves, which is not that far off from the real number. And that's why we're doing, that's why we end up having to search much fewer things, much fewer locations, is because if we make a move and it doesn't actually lower the amount, then we can immediately cut it off. All right. Okay, so this is starting off pretty well. The min heap, I don't think we're using that anywhere now. I got rid of that and I replaced it with the open set. So we're going to get rid of the min heap altogether, so it's not just hanging out. Then we're going to get rid of, I'm going to wrap this up. We don't need to test the min heap anymore. Oh, well, before we do this, let's go ahead and commit. All right, so we took the A star, we extracted out the thing that actually does that. We replaced this. We put a note that this is broken. The state cost was now added in. Okay, BFS uses open set. Okay, now we're going to get rid of everything that has to do with min heap because we're no longer using it. And hopefully that was it. Just do a build real fast. All right, perfect. We're still building, so let's go ahead and commit that. Min heap gone. Okay. Drop the min heap. Simple. Okay, great. So now we've gotten rid of that. So now we only have open set, and I guess we also don't need this priority queue because we're not using sorted set priority queue anymore either. What is actually referencing this? The test. And the test. All right, so we just get rid of this as well. Delete. Get rid of these because we don't need these. I just deleted the wrong thing. That's not what I wanted to do at all. Trash. Where's my trash? Restore. Delete. Program, we don't need test sorted set priority queue. We don't need that anymore. And then we come down here to where it's all busted. We got rid of that. And then again, .NET build. All right, we got rid of the other thing that we don't need. Now we have no references to this, so we can drop that as well. All right, commit this. Drop the sorted set. Drop sorted set priority queue. All right, let's go ahead and push all of this. Okay. All right, well, that was fun. Let's take a look now at what we have accomplished, what we have not accomplished. All right, so first off, implement the Manhattan the Manhattan distance metric, which I did off stream. And then make the search test unit tests so we can just click on them. That's right. Okay, let's do that next. So this is going to be just a little bit of maintenance work. And then we're going to go back and we're going to spend basically the whole last hour fixing up that open set implementation as best we can, so that when we run the rest of this stuff, it actually looks like what we expect it to look like. Okay. Okay, let's move everything into test. So what I want to do is say new file, breadth first search test.cs, and then this is one thing that I do like about working in Visual Studio as opposed to Visual Studio Code. When you create a new file, it just gives you all of the everything that you want. It's got the namespace correct. It gives you a little class stub and whatever else. I haven't quite figured out how to do that in VS Code. Fast.search.test, and then this is going to using system, using XUnit, using fast.search, and then we want public class breadth first search test face. That's what it is, face. Public void. Let's go take a look at the breadth first search test program. Breadth test solve with a new breadth first search. Okay. Okay. I think basically I want to just copy this. Like this. And then drop it in here. Test state. All right, this is a lot of stuff to keep here. Let's go solver. Goes new. Breadth first search solver. Using system.diagnostics. Using system.threading. Is that must not be what I wanted. Using system.timers. Okay. There we go. Log. That's funny. I use console.writeLine in places. I use log in other places. I don't know. We'll have to fix that up later. But for now, we're just gonna put that like that. Okay, I have no idea if this is gonna work. cd dot dot. Let's give it a shot, right? Passed. I really want the output. That's kind of frustrating. Ooh. So that gets in the way. Let's go ahead and Google that one. XUnit logging. Capturing output. Okay, sure. My test class, I test output helper. Does it just, I guess it just garbages that up on its own. All right, let's give that a shot. Public breadth first search test. And what did this take in? This thing. Okay, breadth first search test. Why does it never work? Okay. Get rid of this. What is this not liking? The type or namespace could not be found. Do you know where it is? Sure. Hey, all right. And then we just want to write output instead of console.writeLine. Reporting timer, start, stop. Console, console. Oh no. Console. For var move and solution. Oh, how about .toString? .toString, I guess. Any guesses on whether you think this is going to work or not? Honestly, I have no idea. I'm going to guess not. Things tend to be more difficult than I expect them to be. Oh, hey, what's up? Hey, that was awesome. You get a little pass message and then you get all your output. Oh man, that made my day. Okay, that was awesome. That's great. Okay. So instead of breadth first search test, do I want to say, what do I want to say here? Because I don't want to rewrite this for all of them. So instead of calling it breadth first search test, let's call it solver test. Man, I'm actually starting to like this. This is going pretty well. Okay, so solver test, and then we want this function called, test breadth first search. And then we want this thing called private void test solver. And then we want this to be I search algorithm solver. And then we can move this up here. Okay, why should this ever fail? That's a great question. So let's put in some conditions and see if we can get it to pass or fail. Okay, solver, new breadth first search solver, test solver of solver. Getting tired of saying solver, that's for sure. What else can we do here? We want to pass in the actual state. Okay. String initial state. And then int expected optimal cost. Okay. Now we want to pass this in. Initial state. And 31 is the optimal cost. And then that is going to replace, I know I had this somewhere down here. Okay, so now what we want to do is say assert dot equal, and this we want to pass in the optimal cost and I. assert optimal cost and I. Optimal solution found. We don't want to put optimal because we're asserting that. Is there like a message? No. Expected. Int precision. No, whatever. Okay, we're just gonna leave it like this. So that prints it out. We're asserting that it is optimal here. It will fail if it's not optimal. I wish I could put a message here. I wish I could put a message here that said it was not optimal. I wonder if I can just do that. No, it's not going to like this at all. I guess I could do an assert true. But I want to know the value. Yeah, let's just do it like that. Assert true optimal cost equals the value. And then for this one, you can put a message, which is found a non-optimal cost. Expected equals plus optimal cost plus actual equals, and then put in plus I. Okay, so that'll tell us when it fails. I think we want to go ahead and put this up a little higher. The reason I used to have this at the very bottom was because I was printing out all of the moves, as you can see right here with this giant. Yeah, we're not gonna actually care about those anymore. Okay. And I want to put this a little further up so that it reporting heartbeat can actually happen right here. And I don't actually care about the time anymore either, because that's part of the reporting heartbeat. No, I do care about the time because it's going to format it a little better. Okay, perfect. All right. Has anyone who's watching ever done search problems like this before? I'm curious. All right, we have now passed in all of this so that there are no more variables in here. So except for the reporting timer, spits out every 10 seconds, but that's about the heartbeat that we want. Okay, I feel good about this. No solution found. I guess we should yeah, how about this? If solution equals, all right, so we're going to have this thing where the optimal cost is going to be -1, and -1 is going to represent, okay, optimal cost of -1 represents no solution, right? I'm never really going to test one of these, but just so that I can clean this up down here at the bottom and actually assert a failure. Okay, so if solution equals null, then what we're going to do is say assert dot true of optimal cost equals -1, and then say found no solution but one should exist. Okay. So this is going to get here. And if it doesn't find a solution, then it's going to say, all right, was there no solution? And if that's true, then this is fine. Otherwise, this will bomb and say, did not find a solution, but one should exist. All right, so we have an assert on every possible path, which I think makes for a better test, one that is not going to just report true all the time, which is great. Okay, that's awesome. And let's see if this runs. Build it. Run it. All right. All right. That's awesome. Okay, we got our time. We got our little printout of number of states per second, etc., etc. All right. All right, this is good. This is good. Let's go ahead and move on to the next one, which is A star. Test breadth first search. Test A star. A star search. Again, we want to test it A star Hamming distance. And this is going to be, should just be new A star search solver with inpuzzle.hamming distance. That's great. That is so awesome. That's so great. And then let's do one more. And this one should be not hamming distance, but Manhattan distance. Manhattan distance. Let's see if this one runs. All right, passed one. Found the optimal. Ran 178,000. That appears to be the same. Ran this last one. Only searched about 7,000 and passed and found the optimal. Okay. This is awesome. Now we get to go back over to this program and get rid of all of this garbage. Okay. Test solve. That's what we got rid of. There we go. Test goal initialization. Let's go ahead and just add new file in puzzle test. All right, this is great. Using system, using xunit, using fast.search, namespace, fast.search.test, public class, in puzzle test, fact, face. I'm really good at typing face instead of fact. Public void test initialization. Is that what it was? Test goal initialization. Looks like we have more than one test here. We do have more than one test. We have like 4 tests here. So let's go ahead and break these up. Test default initialization. Yeah. Or puzzle 3. Oh. Okay. paste, paste. Okay, and then what we want to do is we want to assert assert.true is goal. And for this one, we want to say you know what? That's good enough. Now what I would think we want to do is say size in, and then I think you do something like theory. How do you do this? Let's go to X unit theory. X unit theory. Okay, X unit. Getting started. Theory. Inline data. All right. Theory. Inline data. 3. That's exactly what I wanted, actually. 4. Okay. Let's give that one a shot. Zero passed. It didn't run anything. Error. Test method has the same. Oh, yeah. Test. Are these even interesting to have? Probably not very much. I can't test all states, but I can certainly test a few. Yeah, I feel like we should test a few. Okay, so test, what I want to test is that the initialization parsing. So I want to test that I can actually parse them, which is what this one does. And then here I want to say, give me the output. So I don't actually have access to the internals here, do I? Puzzle3 dot. I guess that's the other thing. To do test move expansion. That's another reason we could screw up. Okay, puzzle 3. To do test that making a move makes a copy. Yep. To do test move, test that making a move results in correct state. I'm not actually going to implement all of these right now, just putting some notes here. I'm going to do this kind of stuff off stream. I don't think it's super important for what we're doing unless it turns out that it's broken, of course. But for now, I am just trying to move the stuff out and see what we have going. So now I want to say toString and How do I want to do this? Because this has new lines in it and whatnot. Really what I just want to do is make sure that the initialization is correct. I guess the way that we could do that is we could just inspect individual locations. Let's do that. Let's make it so that inPuzzle has an indexer. And then let's go through and let's test the indexer. Okay. So we're going to say public int this of int row int call get, and what we want to do is we want to say this dot get index. No, doesn't work like that. Okay, we want to say return this dot board right shift of row times value bits times this dot in plus call times value bits. And what this will give me is ulong item tile value. And then we want to take all of this and 0xff. What is f? That's 15, right? Yeah, ul. And we say return int of tile value. Okay, so now we have an indexer so that we can test the initialization of this. Okay, so now what we want to say is var okay. Oh, okay. Do state string. No. Var var flat equals new. Learn how to type. And then we're just going to copy this. And then we're going to put it here. And then we're going to put a bunch of commas in it. I just can't type today. Okay. And then we're going to say string.join. Wait, let's go with no, I think we want to do this backwards actually. Okay. var state string. And then we want to say flat equals state string dot split on space dot select int dot parse dot to array. And now what you need is using system.link. Okay, now we have both of those, and now we can say our puzzle 3 for int row equals 0, row less than 3, row plus plus, for int call equals 0, call less than 3, call plus plus. And then we have int expected. No, I equals 0. Assert dot equal of flat of I. That's what we expect. And the actual is puzzle 3 of row call I plus plus. So we assert that all of them are the correct value. Yeah, let's just see if that works. Wish this would track instead of me having to scroll it each time. Okay, that appears to have passed. Let's go ahead and just put a 1 here and see if it fails. Yay. All right, it expected 6 and it got back 8. Yeah, that's perfect. Okay, all right. Okay, great. Let's run these. Okay, pass 2. Program in puzzle, program, we just did goal initialization. Hooray. So we don't need goal initialization anymore. Now, we want to test the Manhattan distance. Okay. These are also in puzzle test. I guess we should have to do test Hamming distance. All right. Okay, this is great. This is great. Okay. Test Manhattan distance. Again, we want this to be a theory. And then we want string initial state. All right. And then we want int expected. So now what we do is we say var state ooh, fun. Yeah. To do test invalid initialization of state theory. So now you have inline data of this and I forget what it's supposed to be. 21. Sure, 21 sounds right. And now what we do is we say var state equals initial state. And now what we want to do is we want to say size equals math.square root. No. Int in okay, no, 3. All right, do in, and then we have var score assert dot equal of expected and score, and that's it. Let's do inline data and 2 more of these. This is going to have a value of 0. This is going to have a value of 12. Okay. I'm actually really liking this test framework. All of that code became so much smaller and easier. Let's test this one. Pass, pass, pass. Program. No longer need this one. Oh, look at that. We no longer need this program at all. Let's get rid of the whole program. Delete. Yep. Oh, well. Too late. We'll just check it in 2 batches. Okay. BFS test. Oh, I don't want, actually I don't want this. Unstage. Because I called it the wrong thing anyway. I want to call it solver test. Right, is that what we named it? Solver test. Rename solver test. Okay. Back here, refresh. Okay. Move in puzzle test to test project. And move solver test to test project. And then we can get rid of this part, which is no longer want this to be an exe. Let's see if this all works. Build. That's awesome. Well, I certainly have found one thing that I like about unit tests. Can I just run the whole thing? Run all tests. Everything passed. Run all tests. Everything passed. Run all tests. That is so great. That is making my day. Okay, only a couple of things that I want to do is I want to say new file base test. Let's call it base test. Test base. Let's go public, yeah, no, using system, using X unit, namespace, fast.search.test, public, public abstract. I don't even want it to be abstract. Yeah, I do. Abstract class. I want to call this base test base. And then I want to move. It's not going to work like that. That's still kind of frustrating. Okay. Okay. Well, we're just going to do it anyway because I think it's going to make it a little bit cleaner, but I'm not 100%. So first is open set test, and basically, nope, solver test. And basically this is what I want to move up there. Okay, let's get rid of that. 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 Okay. Private read-only. Using. Okay. And then we want to call this test base. And we want to make this protected. And then I want to call this output. Just output. And then I want to say that each of these, I still have to add this to each one. That's not super helpful. Yeah, that's not super helpful at all. I don't know, if there's functionality I want to add, it's just better to have this now. It's gonna save us a lot of time on refactoring later. Ha! Save us time on something we don't even know if we're gonna do. Ha! Test base. Now I don't want this. And now what I want is base of output. Okay, and now we're just going to add that to each one. Solver test. Open set test. In puzzle test. I'm going to call this base test base. And then we're going to use that. And then we're going to go to this and we're going to say test base. And then we're going to add that. And then we're going to try this one more time. Solver test. Run it. Okay. Okay. All right, everything went out. Okay. Refresh. Okay. Refactor fast.search to class lib. Also add test base for all test classes. All right. I actually feel pretty good about all of this. This cleans things up a lot, makes things a lot easier to run. Let's go ahead and just check off the list of the stuff that we did. Make the search test unit so we can just click them. Hooray! Move all of the program stuff into unit test. Hooray! Change the project from being a program to being a class lib. Hooray! Okay. Implement the test in the to-dos, especially, let's say for in puzzle. And then improve the nodes explored by orders of magnitude. Yeah, that's still there. And then the other thing that I think we came up with was, the other big thing is fix the implementation of the open set. All right. Actually feel good about this. Feel really good about this. Let's go ahead and save this as well, and let's drop it in fast. We're just going to call this to do. All right, to do. That's great. Okay. What else are we going to do here in this last like 20 some odd minutes? Well, number one, I got to save this thing off. All the stream graphics going to make its way. Stream graphics. This is going to be a new folder, fast. We're going to call this heuristics. Heuristic visual expansion visual. I know that's really small. Sorry about that. Okay. Takes care of that. All right. What else are we going to do here? That's a great question. Probably, I feel like this is a good stopping point. So I'm just going to talk for maybe 5 minutes about what's going on with this, the direction that it's going. And then I'm just going to end early, I think, today. Get back and do something else. First off, thanks everybody who joined today. Had a lot of fun. Thanks for pointing out that there was a problem on the mobile device. I'll definitely make sure to check that before the next time that I get here. Please check out the code. Please play around with it. Let me know what you think. See if you have any problems running it. Be aware that in the open set there is actually a problem with popping the values correctly. And I think, you know what, that's one thing that I can do in this amount of time, which is we can just do it like this. Okay, pop. No, I don't want pop, I want, okay. Improve works after mini same value. All right, so I think that like the idea here is you have your root node, your min, and it has a cost associated with it. So imagine that there are 3 different states that all have the same cost, and all we're going to do is we're going to pop all of them on. This is a binary tree, so one's going to be on the left, one's going to be on the right, and one's going to be on the top, and they're all going to have the exact same cost. Now, I told you earlier when you search to remove, it searches down only one branch of the tree. It doesn't check all of the values that have the same cost. And so what's going to end up happening is it's going to search down either the left or the right. And if we add 3 with the same cost and then we try to remove one of the 2 leaves, it's not actually going to find it, and it's just going to keep adding values. Like we can keep calling improve over and over, and it's just going to keep adding new values. That is my expectation. So the way that we're going to do this is we're going to create a new open set. We're going to push things with the same value, 5, 5, 10, 20. And then we're also going to push 30. And now what I think is we can keep adding as many as we want with 30, and it's not actually going to improve it. Right? So the idea here is if we add something now and we change the cost, this one should not add to the set. Well, one of these two should not add to the set, so we can definitely find this immediately. So 20, and we want to change this to 6. And what ends up happening here is we just want to check that the set size is equal to 3, because there are only 3 states, 10, 20, and 30. And then we tried to add 20 and 30 again, and I think what's going to end up happening here is this is going to end up at 4. And that's wrong. So improve works after many same value. There we go. Okay, so that is the problem. And we have a failing test case, which we now need to fix. So I guess that's like the point of TDD. Okay, like I said, before I get my brain all in the mode of trying to fix this, I am not going to do that because there's no way I'm going to get this done in like 20 minutes. And so instead, I'm just going to wrap this up. All right, we have a test case that's busted. In fact, we can put this now in the to-do. In fact, I don't even think we need this to-do here anymore. We can put it here. All right, fix test. Okay, improve. There we go. Okay. That's a little frustrating that we have that problem. But once we get that fixed, this is all going to be pretty good to go, and we can start grinding away on actually making better and better heuristics to show further how much improvement we can get. We'll also ramp it up to be a 4x4 instead of a 3x3, which has, you know, hundreds of billions of states. Not so much that you can't keep it in memory. Actually, that's a great question. Can you keep it in memory? 16. It's 16. Clear 16 exponential. That is how many states divided by 2. So there is roughly, what is that? Million, billion, million? No. Tens, thousands, millions, billions, trillions. So there's roughly 10 trillion states, valid states in the 4x4 puzzle. And what we're going to do is find a way to search through all of those. I mean, this is way too many to keep in memory for obvious reasons. Like even in the closed set, we can't say, oh, we have visited this, we have visited this, we have visited this. And so we're going to come up with ways to essentially estimate whether or not we have seen this before, and come up with better heuristics so that we don't need to search nearly this many states. That's it. That's the plan. So the problem size just went from 180,000 states to 10 trillion states. That's what we're going to ramp it up to. Maybe we ought to do a 3x4 first. What would a 3x4 be? 12 exponential? Okay, this is still significantly more and fits in memory. So maybe we will do a 3x4 first. And then after that, we'll move on. This is going to require some refactoring of the npuzzle class. to not just have, it's going to require refactoring so that in is actually number of rows and number of columns. Yeah, that's what we're going to do. This is great. This is really great. All right, well, again, thanks for joining me. Thanks for pointing out the bug with viewing on a tablet. I will work on that. And in the meantime, yeah, everybody have fun, and we'll see you tomorrow, same time, same thing.